get familiar. So if you don't know by now, then you should probably get familiar.
Hello students, so welcome back to my YouTube channel. So I think this is the video part number 5, right? So in the video part number 4, so we have discussed the acceleration of a body on inclined plane, right? So in two different cases where the inclined plane may have friction, may not have friction. So in both the cases, how we can have the acceleration. Now in this particular video, so I am going to discuss some applications of Newton's law, okay? So of course there are various applications you can see in your daily life about the Newton's law. As per your syllabus, some of the applications to be discussed here in general. Okay, in general means particularly say how motion of the connected bodies takes place. Okay, connected bodies means they are connected by a string, a wire. Okay, and it is hanging over a pulley. So depending upon its weight, how the motion takes place on the system. So that is what you have to discuss here. So in the discussion, you have to find again how to calculate the acceleration, and if it is connected by a string, so how to calculate the tension created in the string also. Okay. So now let us start the first application, that is motion of connected bodies. And there are two cases again, vertical motion and horizontal motion, right? So this is the first case here, vertical motion for you. Okay, now look at the diagram. So we have a system consisting of a pulley fixed to a pivot here, and a string is hanging over the pulley. Okay, you have to take a string and hang over the pulley, so the pulley is assumed to be frictionless. Frictionless pulley will be there. So, and at the two ends of the string, you have to connect some masses here. Okay, like this. So let us say M1 and M2 are the two masses here. Okay. And then when the system is going to be show you the motion. So if there is a imbalance in the masses, if there is a difference in masses, then we can see that the masses will move up and down, right? So now in this case I am considering mass M1 is greater than M2. Okay, means this one is greater than M2. So you can expect that mass M1 is moving downwards, M2 is moving in the upward direction, correct? Okay, then what is the acceleration in the system? The question is, you have to calculate basically acceleration, right? How to calculate the acceleration, and what is the acceleration of mass M1 and what is the acceleration of mass M2? So when M1 is moving down, M2 is moving up, so they are moving with the same acceleration but opposite in direction, correct? So A, you can write the acceleration, downwards acceleration A, and upward acceleration also A. Okay, so you try to understand this diagram in that way. Okay, now the same thing I have written here. If M2 is greater than M1 and the system is released, okay, just initially you are holding the system, the moment you release, how it is moving, M1 move downwards and M2 move upward with the same acceleration A. Okay, here part of the weight M1, so when the system is moving like this, what is the weight of the mass M1 actually? That is given by M1 into G, weight is given by M1 into G. Okay, but it is not moving freely. Part of its weight is utilized in lifting the mass M2. So what is its weight? Its weight is given by M2 into G, So its weight is, is lifting upwards by M1G. So that means its weight is utilizing part of its force to lift the mass M2. Okay, part of the weight M1G is used to lift the mass M2. Clear? Hence, the resultant force acting on the system is equal to M1G. You should write first because it is moving downwards and lifting M1G up. Okay, M2G up. So M1G minus M2G. Okay, if this mass is not connected at all, then you can say it is just moving downwards with the weight M1G. Okay, part of its weight is utilizing to move the mass M2 in upward direction. So you have to minus that M2G here. Clear? Okay, what is common factor? G is common. So M1 minus M2 into G. So acceleration of the system A is equal to now resultant force by total mass. So whatever the force we considered here, that is called resultant force acting on the system M1 minus M2 into G. Okay, divided by just total mass is add the masses m1 plus m2. So that gives the simple formula called acceleration in the system. Okay. Now let us continue. How to find the tension in the string. So what do you mean by tension? So whenever a string is stretched at the two ends, then it is having some tension. Okay. So the tension force acting on the string always. Okay. Now mass m1 is moving downwards. So what is the direction of the tension? So it is moving in the upward direction. Okay. Tension acting on the string is in the upward direction. So even this side also. Okay. So we can see that it is hanging downwards. The tension is moving in the upward direction. Okay. So now let us consider one side to calculate the tension. So this side let us consider. So where m1 is connected to the pulley. So consider the motion of only m1 downwards. m1 is moving downwards. Okay. The tension T in the string acts vertically upwards. Vertically upwards. Okay. Then you should consider m1g as the force minus the tension acting in upward direction minus T is equal to m1 into a. So that gives the motion in the body downwards. m1 into a, where is the acceleration. Okay. So now this acceleration is given by already equation 1. Okay. Now simplify this equation for t. You take the t on the other side, it becomes plus t, and m1g, and take this m1a in the left hand side. So that you will get m1g minus m1a actually. So now from this equation 1 a is substituted here. What is that a? m1 minus m2 into g divided by m1 plus m2, right? Okay. So now the simplification part is, so what is common factor? m1g, and here also m1 into g. So take that m1g common, you left with 1 minus m1 minus m2 divided by m1 plus m2. So m1 plus m2 is LCM. Okay, take that LCM and simplify, you will get the equation for tension as 2 m1 m2 g divided by m1 plus m2. Okay, so that's it. So in this application, basically in the system, how the motion takes place and with what acceleration, okay, how to calculate that acceleration using equation 1. And similarly, if it is connected to a string, so what is the tension created in the string? Okay, how to calculate that string using the equation 2. Okay, so that's all. Now let us consider the vertical motion is over, you know. So let us consider the horizontal motion now. Okay, so connected between the two bodies by a string, with the help of a string. Clear? Okay, so look at the second case, that is horizontal motion. So it is very simple. You look at the diagram. So where we have the two masses again kept on a table. Okay, so we can see that m1 m2 is again connected by a string. So we are considering the system where the two masses are connected by a string, you know. So one of the mass should be kept on the table here, that is, let us say m1, and then the string is passing over the frictionless pulley. So other end consisting of mass m2. Okay, now again depending upon mass m1 and m2, so you can expect that the mass m1 kept on the frictionless pulley is moving in this direction. So moving in this direction like this. Okay, and then the moment you get the pulley, so the direction of tension changes like this. It is now downwards. So acceleration of the body is downwards now. So that means you are assuming that m2 is greater than m1, and hence m2 is pulling the mass m1 over the table. Okay, frictionless table you are assuming. So if there is any friction, you can consider that friction part here. Otherwise, you can neglect the friction. Okay, now how to draw the free body diagram? So you just try to understand the FBD, free body diagram. For m1 first, you see. So m1 is considered here, mass m1. What are the force acting on the m1? So that is what actually you have to show in the free body diagram, right? So first of all, it is moving in the direction of the tension. So T is one of the pulling force here. Okay, tension is the pulling force, and it is opposite by friction. Let us say it is acting in between the two surfaces, small f, you know. So frictional force. If there is any friction, then you have to consider the friction. Otherwise, F is equal to 0. And then the weight m1 is downwards always, that is m1g, and this weight is compensated by always normal force in the opposite direction, normal reaction. Okay, so these are the forces acting on the m1. And similarly you consider m2 now. In case of m2, so it is moving downwards, that means its weight w is equal to m2g, always downwards, okay, and it is opposed by only tension. So there is no horizontal forces at all here, okay, there are no horizontal forces at all acting on the mass m2, okay. So the two forces T and W are acting in the opposite direction on m2. That's it. So once you understand the diagram, now let us see. In this figure 2, the mass m2 is kept on a smooth horizontal table. So, okay, resultant force acting on the system you have to write, you know. So resultant force acting on the system producing this acceleration here downwards is given by, okay, m1g divided by m1 plus m2. Total mass is m1 plus m2 here, moving downwards, okay, moving in a particular direction. And here only you have to consider m1, because so the moment, the resultant force acting on the system is actually on the m1. So there is no force acting on m2 except its weight, okay, no external force acting on m2. So consider only force acting on m1, that is m1g divided by m1 plus m2, okay. So considering only the motion of m2 now, okay, motion of m2. So we have the tension in the string is given by just T is equal to m2 into A. So this side I am considering, okay. So we have to calculate the tension at one side. So only the motion of m2 you consider, then tension is given by m2 into A, moving with the acceleration A. So because the only force acting on m2 is now is the tension. What is the force acting on m2? That is only tension. If the tension is released, means if you cut this string, it will fall down freely, okay. So otherwise it is acting or opposed by tension. That is only the force acting on the m2, okay. So then calculate the tension T is equal to, as per this equation, m2 into A. From equation 1 substitute that A, m1g divided by m1 plus m2. So that gives the equation for tension, and this is the equation for acceleration of the in the system. That's it, okay. Okay, now look at the next particular case where motion of two bodies connected by strings, okay. So now in this particular example, you have to consider the two masses connected by a string in between, okay, and then our intention on the system is to move both, okay, both m1 and m2 should move. That's why we are connected the two bodies by a string. They are separated but connected by a string, okay. So in order to move both the masses m1 and m2 in the right side direction, so we are applying the force F. So this is the applied force. So the force is applied on the mass m2 only. You have to remember that force is applied on mass m2 only to pull, okay. So automatically we can expect that the mass m1 is also moving. Why? Because it is connected by the string here, okay. Applied force is acting on m2, and whereas the tension in turn acts on m1, so that both the mass m1 and m2 are moving in the right side direction. Clear? Okay. So now look at the free body diagram on m1. So one of the force acting on the mass m1 is tension, and the weight is in downward direction m1g, and okay, so this is n normal reactions in the upward directions on both the masses, okay. So here it is on the mass m2 only, we can see that there are four forces, okay, applied force, opposite the tension, and weight, and normal reaction. Clear? Okay. Consider the two bodies of mass m1 and m2 connected by a string and pulled by a force F. Okay, then we have separately for m1 and m2 you have to look at the equations. So for m1 there is a force acting on it is T. Okay, T is equal to, okay, m1 into A, because it is moving with the acceleration, moving the system is acceleration A. So m1A. And then look at m2. So there is applied force opposite by tension. So F minus T you have to see. F minus T is equal to that m2 into A. So making the body to move with the acceleration. Both are moving with the acceleration A. So you should write m1A and m2A. Okay. So where in this above equation T is the tension, and substituting the tension from equation 1, okay, in equation 2. So just you see T is equal to m1A. So you can substitute here, right? So F minus m1A is equal to m2A. Simplify the equation for F. So you take this m1 on the right hand side, and take A common. So then you will get A into M1 plus M2, equation 3. Okay, so if we simplify again for A, okay, by cross multiplication, A is equal to F divided by this M1 plus M2, right? So acceleration equation is given by equation 4. So again, if we substitute back the equation A, acceleration equation, so into the equation 1, right? So putting the value of A in equation 1, you will get the tension equation, right? T is equal to, say, M1, A is substituted here as, okay, F divided by M1 plus M2, okay, substitute here in place of A, that is F by M1 plus M2, you will get the equation for tension. M1 F divided by M1 plus M2 is the equation for tension. Now, what is the force acting on M2? So, only F1, applied force F is acting on M2, so in the forward direction, whereas the tension T is acting on M2 again in the forward direction, so that the system is moving in the forward direction. Clear? Okay, now look at the next example, motion of bodies in contact. So, it is like this. See, there are two masses M1 and M2 kept in contact. Okay, then you have to apply the force to get the acceleration on the system. Okay, so let us say in the first case again, when the force acts on the body of mass M1, where is M1? So, we are considering this mass as M1 here. On that, the applied force F in the right side direction, so that the entire system is moving with the acceleration A bar in the right side direction because of the force. Okay, so both M1 and M2 are moving here, right? If there is a gap, then M2 is not affected, only M1 is moving. Okay, so in this case, there is no string between M1 and M2, but M1 and M2 are in contact, so that whatever the force applied on M1, so that also gives impact on M2, so that both M1 and M2 are moving together with the acceleration A bar. Clear? Okay. Now consider the two bodies of mass M1 and M2 put in contact on the table. Okay, if a force F is applied on the mass, particularly M1, we are applying the force on M1, you should remember, then equal acceleration is produced in both the bodies, that is A bar. Okay, so how do you calculate that acceleration? Very simple, you just calculate acceleration according to Newton's law as the applied force divided by total mass. It is just like a single mass, right? So M1 plus M2 you have to consider. So A is equal to F by M1 plus M2. If the force exerted by M2, okay, now you have to think that what is the role of M2. So when both are moving, of course, in the forward direction, the force is applied on M2, M1. So M2 is also exert some force, but in opposite direction, isn't it? It opposes the motion with the force F dash, let us say, in the opposite direction, right? So if the force exerted by M2 on M1 is F dash, then the difference, that applied force, should be subtracted by the opposing force F dash. So F minus F dash is equal to M1A now. Okay, so simplify for F dash now, that opposing force F dash is equal to what now? So F minus M1A. Okay, so this is just simplification by rearranging the equation. So F dash is equal to F minus M1A. Substitute the equation of A from equation 1, that gives M1 into F divided by M1 plus M2, and you take F common, then you will get 1 minus M1 by M1 plus M2, and LCM is M1 plus M2. So if you take LCM M1 plus M2 and simplify, you will get this equation 2, that is F dash is equal to M2 into F by M1 plus M2. Okay, the opposing force to the motion. Clear? In the same example, I can consider, suppose if the force is acting on M2, okay, let it be second case, when the force acts on the body of mass M2, then what changes you have to do? Look at the procedure here. So now the force applied is here F, and there is opposing force now F dash on M2 by M1, correct? Okay. In the same example, acceleration is now in the left hand side direction, that's it. See, like this it is moving. Assume that the system is moving in the left side due to the applied force here. So that is given by, so again A is equal to F by M1 plus M2 only. If the force exerted by M1 on M2 now, isn't it? It is reverse, is F dash. Then F minus F dash is equal to what you will write? you should write in place of M1 you should write M2. Okay, because opposing force is acting now on M2 by M1. Okay, so substitute this M1 in place of M1 as M2. So that is F minus M2F by M1 plus M2 from equation 1. Clear? So then here also 1 minus M2 by M1 plus M2. Then by cross multiplication you will get here in place of M2 you will get M1. M1F by sum M1 plus M2 is the opposing force. Clear? So that is the difference you will see in the second case. Okay, so these are the important applications in general according to Newton's second law. Clear? So I will see you in the next video. If possible, I will solve the problems on this friction. Okay, and there ends the chapter friction for you. Clear? Okay, see you in the next video then.